All right, let's go.
Awesome. So yeah, I'm Madison. I'm a mid-student right now. My background's actually in political science, so this has all been new to me. You want to explain about it?
And once again, I'm Mike. I have a background in computer science, really interested in machine learning. I work at IBM as a machine learning engineer, and I focus on algorithms, particularly in the distributed case on Apache Spark and Apache SystemML. And so, and background-wise, I'm particularly interested in medicine, applications of medicine. I was actually in medical school for a couple of years, ended up getting involved in research involving machine learning and medicine in the emergency department. Ultimately, we decided to shift gears a little bit more towards a machine learning-oriented focus. So today, we want to just present on a project we've been working on, which is predicting breast cancer proliferation scores using this project called Apache SystemML and Apache Spark. And so overall, maybe a few key takeaways. And so if you're particularly interested in this domain, I hope it's an interesting exploration of what we worked on. Maybe more generally, it can serve as a nice use case of going from a smaller scale example and scaling it up to a larger case, a follow-up study, more data, perhaps in a distributed sense. Maybe a final takeaway, too, is just having a clever understanding of your data and not just viewing it as numbers, but really understanding where it comes from, what the assumptions are in practice, can allow you maybe to manipulate it to make it easier to actually apply machine learning, so make a more tractable ML problem. All right, so we talked about who we are. So basically, we like health and we like data, right?
All right, so we were looking at how do we combine big data and health, and how can we do it publicly because we're open source. So we wanted to make a use case for work, but it's a little bit difficult finding medical data that you can share. So this is a little tricky. We came across the Breast Cancer Tumor Proliferation Challenge, where they put a challenge up. They're like, here are 500 images of breast cancer tissue. They were actually biopsies, so the tumor was cut up in slices and put on an image and taken with a microscope. They said, okay, with these 500 images, can you actually predict what score the tumor is? So we decided to take on that challenge. And then, if you don't know, some context, just briefly. So breast cancer is the leading cause of cancer for women, and obviously early detection is a better outcome for everyone. So the problem with this is predicting the score or determining the score is very tricky, even for trained pathologists, because it's really subjective. So we're going to show you an example image, and you can easily see that it's kind of tricky to discern everything. So if we developed an algorithm that could predict this for pathologists, it might be easier in determining what score the tumor is and lead to earlier treatment.
So just to look at this image real fast, just so we know what we're talking with. So once again, right, like Madison said, you've got this tissue that's been biopsied, it's sliced up, put on a slide, and put under a microscope. So what you're looking at is actually stained tissue. And so the white area is the slide in the background. All this blue and pink stuff is tissue that's been placed on it slightly. And it's stained to actually show up different cell organelles. And in its image, it's manually you would do a microscope as a pathologist, or you could image it to be extremely high resolution.
So this is the zoomed up image. The images are really, really big, lots of pixels. So this is just one tiny zoom up image, which you can see up at the top where it comes from. So we're looking at the nuclei, and we're trying to determine how fast it's spreading and how much the tumor is growing. So you can see we're looking for the nuclei characteristics there.
And so, overall, in actual practice, right? So a pathologist, which is once again, it's a medical physician, MD, DO. They would look at this. They'd look at this tissue, and they would examine multiple areas of the tissue, right, to try to find probably the best areas and just make sure that it's uniformly kind of spread out across the whole tissue. And they would do these three different criteria, with the red one in the middle being the one that we're particularly focused on. And so they would examine. They would decide which of these three categories, 1, 2, or 3, that their observation fell into. They'd assign that score to it. And ultimately, along with these A, B, and C, they would actually assign a grade to the cancer. And so score-wise, 1 is the best prognosis, right? So you're thinking more on the edge of more benign tumor, whereas 3 is a much worse prognosis, so more of a malignant tumor perhaps, right? So of course, like I said, grade overall is based on a few other things, but the score itself is very related, right? So it's a very good indicator of how bad the tumor is, more or less.
All right, so our goal was predict the tumor score from the slide images we were given.
Right? So easy, right? So where do we start, right? So you jump in, a bunch of data scientists, you got data, no problem, right?
So here were our blockers. So we're using really, really large images.
Which is quite scientific to say.
Yeah, this is a scientific term. And then at the same time, we had a limited number of images. We only had 500, which, when you think about it, is a little tricky.
And then probably the third issue is, more you maybe say it's an issue, is for this type of task, this kind of image classification task, in the literature for machine learning, the kind of state-of-the-art model are these deep convolutional neural nets, right? So we talked a little bit about that, and we'll go into more depth a little bit later. So I want to pull up, kind of like highlight what the issue is here, right? So you've got a limited number of really, really, really big examples, right? And then you have a type of model that can do really well, but it's ideal to have much more data, right? So this is not a very tractable ML problem as it's presented. Ideally, you would have a large number of images, and they'd be relatively small, so that your input dimensionality is not massive compared to the number you have, right? So as it is right now, it's not going to make for a good problem. So
seriously, where do we start?
So we came across a paper at about the same time I came across the challenge, and it was a paper last year out of a group in Stanford, and it was titled Automated Grading of Gliomas Using Deep Learning and Digital Pathology Images. So definitely feel free to look at the paper. It's quite interesting, but we'll pull out the overall theme of what they did. So similar scenario, so automated grading. They were just determining the grade of tumors. Glioma is a brain tumor, so we have breast tumors in our case here, but they had brain tumors. Deep learning, they were using these convolutional neural nets based on kind of the literature for them being a good model for this type of task. And digital pathology, so same kind of images, high resolution images taken under a special microscope. So their approach was this. So they said, okay, in real practice, right, the assumption is that by the physician that this piece of tissue is from the tumor. And the assumption is they examine all over this image, and so they assume that the tumor is uniformly of the same score, right? So they say, okay, well, if the whole image is of the same score, why don't we just chop this image up into smaller pieces, assign the label from the overall image to each individual small piece, and then use that data set as your training set. So basically, cut up the whole slide image into these smaller square tiles, which should be at a certain size that a physician themselves would actually use. They would look at this size tile, and they'd filter it out to remove any areas that didn't have tissue, right? So if it's blank, empty slides where there just wasn't tissue, they don't want that in the data set. So once they have that, and they filter it out, and they've got good tissue tiles, right? They cut it up a little bit further to make for a more tractable problem. So just smaller samples, a little less computationally intensive. And then they assign the score, the label from the overall image to the individual samples. And then they repeat that for every image they had. And so at this point, they've got a data set of labeled samples. So now they have that large data set, a large number of examples, where the data is now much smaller. The individual samples are much smaller. So you've kind of turned that problem where you had very wide examples, very large images, and only a few of them, to now having much smaller images and a lot of them. And so then they trained a convolutional neural network, which is kind of a state-of-the-art model for this type of task, and they got good results. So I'll definitely refer you to look at the paper for more details, but that was their overall approach to this problem.
But in our case, they had 20 images, 20 slides, and we had 500. So we had to alter it, and it's also breast cancer.
Mm-hmm. And if you look at these slides, like we said, they're really high resolution. So once you open them up, each individual slide could be 15 or 20 gigs a piece, right? So at 500, that you could talk about potentially 10 terabytes of data. Right, so needless to say,
a lot of data.
Lots of data.
So our approach was to utilize Apache Spark to cut and filter all 500 slides. And just because they're so extremely high resolution, this is why we're applying it. So it's 4.7 million smaller samples after we cut it up. And we're going to give you an example of how we did that in a second. And then we utilized Apache SystemML on top of Spark. And we're going to go over what that is also. Which helped us do the machine learning on such big data.
Mm-hmm. So hopefully you can see this is following up with a study with what would be the next step, right? You get large amounts of data, you try to validate what the study got, hopefully maybe even get better accuracy. And so this is a natural progression. In this case, the amount of data would suggest that a more distributed approach would be better than perhaps a single node. So
after pre-processing, we had over 7 terabytes of data, which is a lot to work with.
Yeah, not quite a laptop problem anymore.
Yeah, no, we couldn't do it locally anymore.
So real briefly, let's talk about Spark. So we don't make any assumptions. We'll talk about Spark and SystemML. So At a high level, real quickly, Spark is basically this engine for large-scale data processing. So it's distributed cluster-based processing of data. You've got machine learning and SQL and streaming and graph structures and just other, I guess, complex analytics, if you will. And it extends Scala idioms. So if you're familiar with like functional programming or the idea of applying mathematic operations or functions in general to collections of data, they have that idiom and just spread out amongst the cluster. They also have R and Python data frame idioms spread out once again across the cluster. And there's APIs, and overall it's simple to use. We'll definitely more information on the website.
I mean, how many of you have taken 205 if you're a student here? Okay, so we know what we're talking about.
Okay, awesome. Okay. So then Apache SystemML is another project that's a machine learning system for running basically distributed linear algebra on top of Spark. So Spark has this nice idea of distributed data collections, like lists and stuff that are distributed. Doesn't have yet a really good linear algebra story. So SystemML basically aims to be a project that allows you to write the linear algebra like you would write on paper and then write in Python, so matrix-based math. And then SystemML can take that math and just run it on top of Spark with whatever size data you have. So we kind of pull out the linear algebra from R and Python and expose that. And then we have APIs for Spark and Python, Scala. So more information, but real quick, a fun little diagram here. Data scientists write their stuff in R and Python. And more traditionally, you would then try to translate that to more distributed data collection in Scala or Python for Spark, and then try to iterate, where SystemML just lets you go from the math straight in. So it's an ideal use case for this problem.
Especially for people who don't want to do complex systems things and just write the code and do the math. It's a lot easier.
Yeah.
All right, so our pre-processing. This was important for multiple reasons. We wanted to take the approach as the paper, but we also had to kind of filter out this background here, as you see. That's not tissue. And so we couldn't train our model with it because that obviously would throw everything off. So our first step was to cut it up into different tiles, so 1024 by 1024 by 3 pixel tiles. And then that's an example of what the tile would look like, so it's a zoomed-in version. And then, as I mentioned, now that we have the tiles, we have to filter out the non-tissue, which was a little trickier than we initially thought because we had some shadows. So when the tissue was cut up and put on the slide and taken with a microscope, you have a lot of other issues. There were like spills, there was ink, there are shadows. So we have to figure out, okay, how do we get rid of this? What's tissue, what's not? And this is an example. So we actually used thresholding to close the small gaps. And we also had the issue with adipose tissue, which looked white, which was the same as the background. So it's a little tricky. So this is an example of almost 100% tissue. And it would be, the black will represent the tissue. So it shows right here. And then if it was 90% or more tissue, we would keep the tile.
So needless to say, it's a way of basically making sure you take your dirty data and clean it along with the pipeline. Otherwise, no fancy algorithm is going to help, right?
And then after we had the tile, we actually cut it up into 4, and then we have the tile samples. And that's actually what we trained our model with. And so these samples were 256 by 256 by 3.
And these sizes all come from the paper. And the tile size, like we said, is the size that a physician would use when they're evaluating a section of the slide. And then the smaller samples are just to make the problem more computational and to also extend the data. Once again, kind of using the assumption that the tumors uniformly have the same score, so you can manipulate the data to try to make it more tractable. So this is just an example of our code. We won't go too much in depth in this talk. But more or less, at the high level, this is the Spark code for it. So you kind of start with all the slide numbers, 1 through 500. You map those out to all the locations of tiles. Then you map those locations to actually extracting it. So now you have kind of placing the parallelism on the tiles themselves. And then you have filtering, and then you cut them up into samples. And at the very end of this, with some more manipulation, you end up with a big Spark data frame, which contains the label and the associated sample for each row. And so this is, in our case, is about 4.7 million rows. And what you don't see on this slide is the next step would basically take that data frame, save it to HDFS, and then you have it. So you have a 7 terabyte data stored. And on about 10 nodes, this can take 6 hours. On 28 nodes, it takes about 3 hours, so you can extrapolate. It's just overall, it's a nice case for going a more distributed approach. So on to the good stuff, right?
Yeah. This is what Mike was waiting on the entire time we were pre-processing.
So like we said, for this type of task, we used a convolutional neural network, right? So this does fall into the kind of realm of deep learning, if you will, which is more or less just a model that takes into account the kind of spatial structure of images, and it's been shown to have really good results, state-of-the-art results in this domain. So for computer vision tasks, so this is classifying images, like what is this image of, or what objects are in this image, where are the objects in the image, et cetera. And so in addition to computer vision, it's also had really good results in audio, such as like speech recognition, as well as other fields too. So certainly they are somewhat black box, but there's been a lot of work as well into understanding what they do. So I think for the particular problem, they're really useful. We won't go in depth in this talk exactly what they do, but more or less this is a diagram of them, and they're loosely inspired by the kind of visual cortex in humans, with the idea being that if you have an image, and say it's of a bird, and you want to be able to classify, is this a bird or not, right? Your model should be able to classify that regardless of where the bird is in the field, in the image, just like as your visual system. You can identify a bird regardless of where it is. And the multiple layers as well kind of slowly build up this representation. So earlier layers may just be able to find shapes and objects, and not objects, but shapes and sides and edges. And then later on, as you progress into more and more representations, the highest level understands if it's a bird or not. So more or less it just kind of condenses maybe hand-tuned feature engineering into the model itself. So remember, we have large data, right?
Yeah, we're just really emphasizing that.
So in our case, while we could have used a more single-node approach on the smaller amounts of data, we did actually use Spark and SystemML for this. So it's hopefully a good use case of when maybe that might make sense. So we won't go too much in depth, but this is actually the code in SystemML for our ConvNet. And in this case, we have a deep learning library we've written in SystemML that contains all the math. And in this case, if you went into this more depth, you'd see that there's basically a matrix X that comes in, and so that would be supplied with your 7 terabyte data frame on Spark. But within SystemML, you just treat it as a matrix, and you would send it through all these different layers for transformations. And each layer just works with these matrices using basic linear algebra constructs. So you see you go through this forward pass, you end up with a set of probabilities based on what score this sample is of. And then we compute derivatives, and further down, we would actually optimize the parameters in the model. So won't go into too much depth, but just the idea that you basically would write it like you would write on paper or on Python. And then to actually train it with PySpark, and this is our API, so once you have this model written, you can call it passing in data frames X and Y and X validation, et cetera, and ultimately get back the model parameters, which you can then use later on for predicting. So the idea is you have this model that's written mathematically, and you pass in whatever size data frame you have, and it will SystemML will take care of it. So it's a nice approach for this type of problem.
Okay. And then the entire pipeline altogether, we had a lot of steps. So just going over it again. We took the whole slide image, and we broke it down into tiles based off of the paper we read. We thought it was a great approach. And then we took the tile images and divided it into tile samples. We took those sample images and we put it into our convolutional neural net, where we developed the tumor proliferation score. So basically, the model was training and learning how to detect what score it was at. So at a high level, that's what was going on.
Yeah. And so this is still ongoing. So we've got the pre-processing done. We've done more smaller scale testing to make sure it works. And we're still in the progress of actually scaling it up completely. But hopefully, takeaways here, like I said at the beginning, is if you're interested in this particular domain, hopefully this is an interesting approach to this type of problem. And maybe you could take it for any other type of cancerous tissue. And more generally, is a nice case study for going from a more small-scale use case, maybe one you've done yourself or that you've read in the paper, and following it up with a larger-scale validation-type study, right? And then finally, maybe it's the idea that if you understand your data and where it comes from and kind of the assumptions behind it, you may be able to manipulate it so that you can have a more tractable ML problem without really messing up kind of the assumptions behind the data. So at this point, we'd like to take any questions.
Madison, thanks so much. Let's take a question. I'll come to you next. Let's take one right at the back there first. Yes.
Oh. Hi, thanks. So you said that like you have one single score for the whole image, and then you tally it up. So when I'll give you a test image, you're also going to tile up the image. What happens if have you thought if each individual tile will give you different scores, how you're going to find the total score for the image?
Yeah. So that's a good question. And I'll just rephrase that again. So the question is, during training, we take these overall images where it's one label for the overall slide, and then we chop it up, we assign the label to every small sample, and we train on that. So then at test time or prediction time, what do you do? Right? So we would do the same thing. We would take the overall massive image and we'd chop it up into these small samples and produce scores for each sample, right? So at that point, you'd have predictions for each individual segment of the image, right? So then there's a few different approaches you could take. You could take more of an ensemble of them. So you could take perhaps what is the average score, right? You could take perhaps what is the max score. You could even perhaps visualize areas on the slide that have a higher score and then follow that up with a perhaps physician intervention if the slide is not uniform. So in that case, I think you really want to start thinking about what is useful in the actual domain. So I think one step is getting the score, and that's the ML part, right? But then understanding what to do with it is where you're going to go back to medicine. So for example, if part of your image is a 1, or most of your image is a 1, which is a good prognosis, but then there's an area that's a 3, or so the model thinks, right? And a 3 being the worst prognosis, but there's only a small area. An average might just say it's 1, but medically, you would rather go for the 3, right? So that you're quite sensitive, so you're increasing your sensitivity so that you catch that. So you'd be better off catching the bad case than just assuming the least case. So I think you would train on it like this, normally, mathematically, with the labels. But then when it comes to actually what you want to do with it, you want to validate that with a study and based on what's actually good for patients in this case. So there's a few different things. It's a good question, and it would be a nice follow-up.
So I actually had a related question. You mentioned that the scores can be kind of subjective when a physician's actually looking at this biopsy. So two things. Is it pretty guaranteed that all of the image should have one label, like that the progression? I guess this is one sample from a particular patient. The second one would be, do you know about the quality of the data? It's part of a competition, so I'm sure it's been cleaned, but did they elaborate or
Yeah,
to that?
good questions, yeah.
That's a great question.
So for the first question, right, is the assumption, right, is the entire tumor going to have that same score, more or less, right? So if you look in practice what they do, kind of going back to what are the assumptions that a physician makes in practice is they biopsy it, and the biopsy is from the tumor, and they look at it and they examine multiple locations. So it's not a single location that they'll examine. They will examine multiple, and that's part of the actual guidelines. If you got into the guidelines, you'd see, well, you have to do X number of these locations, when the location would be the size of one of these tiles. So based on that, the assumption even a physician makes is, if I look at multiple places, they should all be more or less uniform. So it is an assumption, though, and so perhaps as well you could get a biopsy that nicks some of the tissue outside of the tumor, right? So sample-wise, you may get a sample that's not tumor. So in that case, you still hope that most of your tissue is of that score. And then it kind of goes back to the previous answer is even if one spot doesn't come out with the right score, for example, hopefully overall at predict time, most of the tissue will have a correct score, and so you'll be able to predict still. Now to answer your second question about the data, so it is subjective on an individual physician level. And so for this challenge, right, and this data set, which is actually a public data set on a government site, they did actually get a team of pathologists, and so they did more like a voting on what's a good score for this. And so you'd find that in the medical domain, data is not plentiful, but what they will do is they'll take good samples they have, and they will make sure that there's a good agreement on what a good label for that is, and they'll use that for education. So in our case, we're using it to educate a model, but in real life, they would use that to educate actual physicians and residents and medical students. So in this case, we hope this data is less subjective, just due to the fact that it is an ensemble of physicians that actually created them.
Thanks.
Thanks.
Question right there, Monica.
What were the output unit you used? Did you use softmax or any other function?
Can you say it again?
I mean, for the CNN, what were the output units? Did you use softmax or?
Oh, yeah. Yeah, good question. Yeah. So for the output of the CNN, it's just like a standard multinomial logistic regression, so a softmax output. and we did it over 3 classes so that it's normalized to probabilities of each class. So we say kind of loosely that it would output the score, but in practice, actually, you're outputting 3 probabilities to add up to 1 for the probability of each score. So maybe it outputs 20% of one, 40% of another, et cetera, right? And usually you would take the max of that as the score, but yeah, we did use a softmax.
Let's take one final question. We'll be brief.
Hi. My question is about the pre-processing, the tiling part, because I was thinking, is it possible some tiles, you happen to cut the rich information like in half? So when the tiling process, why not use a convolution-like, have overlapping tiles or randomly sample from the image rather than rigid tile system for all of the original images?
Yeah, so that's a good question. So the question kind of is, why use the tiles that are literally right next to each other and cut up versus overlapping or more randomized? So for right now, starting out with, we did do the individual samples next to each other. But the next step would actually be to scale up that even further. And so extract these tiles plus ones that overlap, and additionally start rotating tiles and even just pull them randomly so that you could generate more data. So I think it's a good idea for sure. And while we started with this, right, we'll start with the 7 terabytes. We could easily scale that up, I think, to hundreds of terabytes. Just going to be computation power.
It's really big data.
Right. Madison, Mike, thanks again.
Thanks.
So
Thank
much.
you.